Hello everyone. Today we are going to analyze this cantilever beam. In this beam we have uniformly varying load. It varies from 0 in the free end to W in the fixed end. The span of the beam is given as L. In the fixed end we need to find the vertical reaction RA and the moment MA. Let us apply the rule sigma V is equal to 0 and find RA. RA is acting upwards, so it will be positive. UVL is acting downwards, so it will be negative. For the UVL, we have to take the area. We know that it is a triangle. We know the formula to find the area of a triangle, that is half into BH. Here the breadth is L and the height is W. So the area is half into L into W. In this way, for the reaction RA, we will get WL upon 2. Now we are going to find the moment MA. It will be acting in the anticlockwise direction. To find that, we are going to take moment about A from the point B. In this case, we have to follow left-hand side rule. Clockwise will be negative and anticlockwise will be positive. The UVL is acting in the clockwise direction, so it will be negative. For the UVL, we have to multiply the area with the centroid distance. The area we have just before seen how to find. We know that in this triangle, about this height, the centroid distance is 1 by 3 into breadth, and towards this point is 2 by 3 into breadth. We are taking moment about A, so we have to take the centroid distance about the point A, that is 1 by 3 into breadth. Here the breadth is L, so it is 1 upon 3 into L. MA is acting in the anticlockwise direction, so it is positive. In this way, for MA, we will get WL square upon 6. Now we are going to find the shear force values. I am going to find them from the point B. In this case, we have to follow left-hand side rule, upwards negative and downwards positive. In the point B, there is no load, so the shear force at B will be 0. In the point A, there is a vertical reaction, so we have to find the shear force values 2 times at just to right of A and at just to left of A. First, let us find at just to right of A. At just to right of A, we have the UVL. It is acting downwards, so it will be positive. For the UVL, we have to take the area. We know the area of the triangle, half into L into W. Now let us find the shear force at just to left of A. With this, we need to add this. The reaction is acting upwards, so it will be negative. In this way, for the shear force at just to left of A, we will get 0. Now let us see how to find the shear force at any section from the point B. We need to find this height. For the distance of L, the height is W. So for L, it is W. I need the height at the distance of X. So I need to multiply with the X. In this way, we will get the height as W upon L into X. We need to find the area of this triangle. We know the formula half into BH. Here the breadth is X and the height is W upon L into X. So the shear force at X will be Wx square upon 2L. Here you can see the shear force diagram. Now let us find the bending moment values. I am going to find them from the point B. In this case, we have to use left-hand side rule. Clockwise will be negative and anti-clockwise will be positive. In the point B, the bending moment will be 0. Since in the point A, there is a movement, we have to find the bending moment at just right of A and at just left of A. Let us find the bending moment at just right of A. At just right of A, we have the UVL. It is acting in the clockwise direction, so it will be negative. Then we have to multiply the area of the triangle with the centroid distance. The area of the triangle we already know, and the centroid distance about the point A is 1 upon 3 into L. In this way we will get minus WL square upon 6. Let us find the bending moment at just left of A. With this we have to add MA. It is acting in the anti-clockwise direction, so it will be positive. So the bending moment at just left of A is 0. Now let us find the bending moment at the distance of x from B. We need to multiply the area of this triangle with the centroid distance. This is the area and this is the centroid distance. In this way we will get minus W x power 3 upon 6L. Here you can see the bending moment diagram. Using the bending moment diagram, we can find the slope and deflection in the point B. We can use the moment area method. First, let us find the slope at B. The formula is area upon EI. We know that this is the cubic curve, that is the third degree parabola. The area formula is 1 upon 4 into BH. Here the breadth is L and the height is WL square upon 6. So this is the area. So the slope at B will be WL cube upon 24 EI. Now let us find the deflection. The formula is area x bar upon EI. The area just before we have found. We need to only find the centroid distance. The formula to find the centroid distance about the point B is 4 upon 5 into breadth. Here the breadth is L, so it is 4 upon 5 into L. For the deflection at B, we will get WL power 4 upon 30 EI. Alternatively, we can use Macaulay's method and find the slope and deflection at any point of the beam. We have to make a section. I have made a section at a distance of x from the point B. We need to find this height. I have already explained how to find the height. We have got W upon L into x. In this section, we have to find the moment from the point B. That also I have already explained previously. For that, we will get minus Wx power 3 upon 6L. Now we can equate the moment with EI d square y upon dx square. We need to integrate both of the sides. When we integrate this, we will get this. To integrate x cube, we can use this formula. For the integration of x cube, we will get x power 4 upon 4. C1 is the constant. 6 into 4, it will be 24. Again, we need to integrate on both of the sides. When we integrate dy upon dx, it will be y. When we integrate x power 4, it will be x power 5 upon 5. In this term, there is no x, so we have to multiply with the x, that is the integration. C2 is the new constant. 24 into 5, it will be 120. In the point A, we have fixed support. In the fixed support, there will be no slope and deflection. So when x is L, the slope dy upon dx will be 0. And when x is L, the deflection y will be 0. In this equation, for x we can apply L, and for dy upon dx we can apply 0. In this way we can find C1. Now let us take this equation. For y we can apply 0, and for x we can apply L. Also we can apply C1. In this way for C2 we will get this. In the slope equation we can apply C1, and in the deflection equation we can apply C1 and C2. First let us take the slope equation. We can take W upon 24 outside, and we can take EI on the other side. It will come in the denominator. This is the equation of slope. Using this equation, we can find the slope at any points. We know that at the point B, x will be 0. Instead of x, we can apply 0. In this way, we can find the slope at B. Now, let us take the deflection equation. We can take W outside. and we can take EA on the other side. It will come in the denominator. This is the deflection equation. Using that, we can find the deflection at any point of the beam. We know that in the point B, x will be 0. Instead of x, we have to apply 0. In this way, we will get the deflection at B. This is the elastic curve. Since there is a fixed support in the point A, in the point A, there will be no deflection and slope. In the point B, we have found the deflection and slope. This is the summary of what we have done. Now we are going to end this session. Thank you for watching this video.